Dear students, I have some questions for you. Why the term mole was introduced? And next, why carbon 12 isotope is taken as standard to define AMU? And how much big the Avogadro number is? What is the difference between specific gravity, vapor density and density? Is there any difference? All are same or different? If they are different, what is the difference? That is my question. And what is the IUPAC standard molar volume for gases? Is it 22.4 or 22.7? What we have to follow for exam? What we have to follow for questions volume? So all these questions are explained in this lecture, and other important concepts in some basic concepts of chemistry and important model questions from mole concept. All these are explained in this lecture. Welcome to our second lecture in some basic concepts of chemistry, mole concept. Our first lecture is laws of chemical combinations. Now coming to second lecture, that is mole concept. So what is mole? Mole is a measure of a substance. Mole is a measure of a substance. So in chemical reactions, we used to study 1 mole of reactant or 2 moles of products. So our discussion is in terms of moles. Mole is a measure of a substance. And it contains Avogadro number of particles. 1 mole of a substance contains Avogadro number of particles. And this mole is giving connection between microscopic particles and macroscopic mass. Mole is a bridge or connection between microscopic particles and macroscopic mass. I will take one example. See, a chemical reaction N2 plus 3H2 gives rise to 2NH3. I am taking the formation of ammonia. Here, this reaction represents 1 mole nitrogen is reacting with 3 mole hydrogen to produce 2 mole ammonia. This reaction represents moles. 1 mole nitrogen is reacting with 3 moles of hydrogen to produce 2 moles of ammonia. So chemical reaction takes place in terms of moles or in terms of molecules, but not in terms of mass. Chemical reaction does not take place in the ratio of mass. It takes place in the ratio of moles, in the ratio of molecules. Right? Suppose if I study this reaction, if I represent this reaction in terms of molecules, 1 molecule of nitrogen combines with 3 molecules of nitrogen to produce 2 molecules of nitrogen. So before introducing mole, the chemical reactions are the concepts studied with molecules only. 1 molecule of nitrogen combining with 3 molecules of hydrogen to give 2 molecules of ammonia. But the individual molecules, counting the individual molecules is very difficult. Because the molecules are very small, it is impossible to count. So, certain amount of substance is taken as mole. Certain amount of substance is taken as mole. What is that amount? For nitrogen, 28 grams of nitrogen is taken as 1 mole. For hydrogen, 2 grams of hydrogen is taken as 1 mole. For ammonia, 17 grams ammonia is taken as 1 mole. So now it is called molecular weight. Ammonia molecular weight is 17. 17 grams is taken as 1 mole. Hydrogen molecular weight is 2 grams. That 2 grams is taken as 1 mole. Nitrogen molecular weight 28 grams. This 28 grams is taken as 1 mole. Right. So why this particular substance is taken as 1 mole? What is the connection between all these weights? Why 17 grams ammonia is 1 mole? Why 2 grams of hydrogen is 1 mole? Why 28 grams of nitrogen is 1 mole? And what is the connection between all these weights of different molecules? That connection is number of particles. In 17 grams of ammonia, we have 6.022 into 10 power 23 particles, which is called Avogadro number. In 2 grams of hydrogen, we have 6.022 into 10 power 23 particles, that is Avogadro number. In 28 grams of nitrogen, we have 6.022 into 10 power 23 particles, that is called Avogadro number. So the common value in all these weights of substances is Avogadro number. Sir, how you can say? How do you say in all these substances exactly how Avogadro number of particles are there? How do you say? See, here I am taking ammonia. So ammonia weight, how much I am taking? 17 grams. 17 grams. And divide this 17 grams weight with one ammonia molecule mass. Mass of one ammonia molecule. Divide 17 grams of ammonia, molecular weight of ammonia, with one molecule mass. You will get 6.022 into 10 power 23. Or take carbon dioxide. Take carbon dioxide, not only nitrogen or hydrogen, I am taking carbon dioxide. So, carbon dioxide molecular weight is what? 44. 44 divided by one carbon dioxide molecule, mass of one CO2 molecule. So, here you will get 6.022 into 10 power 23. So, the same thing we studied in the definition of mole, right? What is that? What is that? Carbon 12, atomic weight is 12. And divide this carbon atomic mass 12 with one carbon atom mass. You will get Avogadro number of particles. Right? So, this is how the mole is introduced. And this mole contains Avogadro number of particles. So, mass of one molecule of carbon dioxide, or mass of one molecule of ammonia, or mass of one molecule of hydrogen, or mass of one carbon atom. So, the individual atoms or molecules mass is calculated by mass spectrometer. Here, carbon 12 atom, mass is 1.99 into 10 power minus 23 grams. One carbon atom mass is 1.99 into 10 power minus 23 grams. That is calculated by mass spectrometer. So, by using mass spectrometer, any atom or any molecule masses can be calculated. How you are getting Avogadro number? Carbon 12 isotope, atomic mass is 12 grams, and one carbon mass, which is calculated by mass spectrometry, that is 1.99 into 10 power minus 23, and this calculation is giving 6.022 into 10 power 23. This is called as Avogadro number or Avogadro's constant. So, not only for carbon 12, so already we discussed what is that? Ammonia. Ammonia molecular mass 17. 17 by mass of one molecule, you will get Avogadro. Hydrogen molecular weight is 2. Divide hydrogen mass with one molecule hydrogen mass, that is Avogadro number 6.022 into 10 power 23. Now, coming to the definition of mole exactly. So, mole is the amount of substance which contains exactly same number of particles present in carbon 12 isotope, 12 grams of carbon 12 isotope. In 12 grams of carbon 12 isotope, how many atoms are there? The same number of particles are present in mole. That amount of substance is considered as a mole, right? Now, mole is just a counting unit. It is a measuring unit. It can be used for anything. 1 mole atoms, 1 mole molecules, 1 mole ions, 1 mole electrons. So mole can be used for atoms, molecules, electrons, neutrons, protons, for anything, because it is a just counting unit. It's like dozen. So 1 dozen, dozen is a counting unit. 1 dozen means 12 items, and 1 score means 12 items, and 1 gross means 144 items. Same as dozen, score, gross. Mole is also counting unit. 1 mole x. 1 mole x means 6.022 into 10 power 23 x. Right? And this Avogadro number is very huge number. It's a very big number. To understand this, write all the zeros: 6, 0, 2, 2, 1, 3, 6, 7, 0, 0, 0, 0, and so on. So it's a very huge number. To understand the hugeness of Avogadro number, how much big it is, one simple analogy. That is, suppose we are spending 1 lakh rupees per day. Per day we are spending 1 lakh. So we have Avogadro rupees. 6.022 into 10 power 23 rupees. To spend Avogadro money, how much time it will take? If you calculate it, the answer is 1.65 into 10 power 16 years. When we are spending 1 lakh rupees per day, it will take 1.65 into 10 power 16 years. That much huge number the Avogadro number is. See, the universe age, the age of the universe is 10 power 10 years. Approximately 10 power 10 years. That means 10 power 6 times it is more greater than age of the universe. So that is the hugeness of Avogadro number. If someone says I am millionaire, what is millionaire? Millionaire means person is having 10 power 6 dollars. If someone says I am billionaire, billionaire means what? The person is having 10 power 9 dollars. So you say avogadronaire. I'm avogadronaire. Avogadronaire means the person is having 10 power 23 dollars money. Right? Suppose if we have Avogadro number of glass marbles or goldies, or Avogadro number of groundnuts. By using Avogadro number of groundnuts, we can cover the whole surface of Earth. The complete Earth surface will be covered by Avogadro number of groundnuts, Avogadro number of glass marbles. So that much huge number the Avogadro number is. Next, coming to atomic mass unit, AMU, atomic mass unit. So atomic mass unit is 1/12 mass of carbon 12 isotope. 1/12 mass of carbon 12 isotope. So this is carbon 12 atom. Carbon 12 atom. So here 1/12th part of carbon 12 isotope is taken. That particular amount is taken as 1 AMU, atomic mass unit. So AMU is a 1/12th portion of mass of carbon 12 atom is AMU. So nowadays we don't call AMU. This is called as unified mass. Both are same. There is no difference. Atomic mass unit only called as unified mass. This unified mass symbol is U, small u. Right. Now, what is the purpose of introducing AMU? What is the purpose of introducing AMU? For example, take nitrogen. Nitrogen, one molecule nitrogen is around 10 power minus 23 grams. One molecule nitrogen is 10 power minus 23 grams. So it is difficult to do calculations with the smallest number, 10 power minus 23 grams, 0.00000 like. Or hydrogen, take one hydrogen. So one hydrogen, it is in terms of 10 power minus 23 grams only. So study and calculations are difficult with the smallest number. So that's why AMU was introduced. AMU is the smallest unit. And 1 AMU is equal to 1.66 into 10 power minus 27 kilograms. Or you can write 1.66 into 10 power minus 24 grams. So this amount 1.66 into 10 power minus 24 grams is taken as 1 AMU. Now we used to measure the mass of nitrogen in terms of AMU. If there is no AMU, we have to say 10 power minus 23 grams of nitrogen molecule, or some x into 10 power minus 23 grams of hydrogen molecule. So this smallest numbers, discussion of smallest numbers is very difficult. That's why we are not using these numbers. We are using AMU. AMU. So individual molecules mass is calculated in terms of AMU. The group of molecules mass is in terms of grams. Right? One nitrogen molecule, what is a mass means it will come in terms of AMU. 1 mole nitrogen, what is a mass? It will come in grams. Right. So now this AMU is our reference. Atomic mass unit or unified mass is our reference. Previously, hydrogen and oxygen are used as references. Right? So I have hydrogen and helium. Earlier, hydrogen is used as reference. Hydrogen is the smallest atom and it has the least atomic mass. Hydrogen is the smallest atom and it has least atomic mass. So hydrogen is considered as reference. Now, how helium mass is calculated? How helium mass is calculated? This hydrogen is taken as 1 unit and helium mass is the number of times it is heavier than hydrogen. So hydrogen is the smallest atom. It has the least atomic mass. This atomic mass is considered as 1 unit, and why it is considered as 1 unit we will discuss later. So this atomic mass, this mass is considered as, mass of hydrogen is considered as 1 unit. Now what is the helium mass means? How many times it is heavier than hydrogen? So approximately it is 4 times heavier than hydrogen. Helium is 4 times heavier than hydrogen, then helium mass is 4 units. Take carbon dioxide. Take carbon dioxide. So carbon dioxide, how many times it is heavier than hydrogen? 44 times it is heavier than hydrogen. So 44 units is the carbon dioxide mass. This is how we have taken earlier. Right? But now this AMU is our standard reference, not hydrogen. AMU is a standard reference. Right? This AMU is calculated from carbon 12 isotope. 1/12 part of mass of carbon 12 atom is AMU. And why carbon 12 atom is taken as reference? What is the reason? Because this carbon has greater stability. Among all elements, carbon has greater stability and its abundance is more. Carbon 12, carbon 13, carbon 14, 3 isotopes are there. Among these 3 isotopes, carbon 12 percentage is very high. Right? And compared to other elements, the periodic table, carbon 12 abundance is more. We know that. And carbon is more stable. Sir, it is fine. Right? Carbon is taken as standard because it is more stable and it is more abundant. But what is the problem with hydrogen? What is the problem with hydrogen? So, hydrogen is volatile. Hydrogen is volatile. This extraction is difficult. Even after extraction, its production is difficult. So compared to hydrogen, carbon is more stable. It is not highly reactive. Easily don't participate in the reactions. So it is stable, non-radioactive and most abundant. So these are the reasons why carbon 12 is selected as standard reference. Anyway, to measure the masses of individual atoms or molecules with the smallest numbers 10 power minus 23 or 10 power minus 24 like that, it is very difficult. So that's why a new unit was introduced, that is AMU. This AMU is calculated by taking carbon 12 as reference. So 1/12 part of mass of one carbon 12 atom is AMU. So nowadays this AMU is called as unified mass U. Molecular mass and formula mass. Molecular mass and formula mass. First see this calculation After that, we'll try to understand difference between molecular mass and formula mass. So see the mass of methane. Carbon 12.011, that is the exact mass of carbon, right? Approximately you can take 12, it's fine. So carbon is 12, hydrogen is 4, 4 into 1. Each hydrogen is 1, 4 hydrogens 4 into 1. So mass of methane is 16. So this is how we are calculating molecular mass. Now if I take calcium carbonate, so calcium atomic mass is 40, carbon atomic mass is 12, and each oxygen atomic mass is 16, you will get 100. So 1 CaCO3 unit mass is 100 U, 100 AMU or 100 U. Right. So what is the difference between this molecular mass and formula mass? Means molecular mass is defined for molecules. Molecular mass is defined for molecules. What are molecules? H2 molecule, O2 is a molecule, CO2 is a molecule, NH3 is a molecule, SO2 is a molecule, CO is a molecule, but NaCl is not a molecule. Calcium carbonate is not a molecule. Calcium sulfate is not a molecule. Magnesium chloride is not a molecule. Ionic compounds are not molecules. Only covalent compounds are molecules. Ionic compounds are not molecules. So they are not molecules. Then what they are called? They are called formula units. These are called formula units. They don't call us. We should not call them as molecules. They are formula units. So what are formula units and why these are called formula units? See this NaCl structure. This is FCC structure, face-centered cubic structure. In FCC structure, one Na plus ion is surrounded by 6 Cl minus ions, and one Cl minus is surrounded by 6 Na plus ions. Right. Now you take one unit cell or bulk of sodium chloride, take the number of Na plus ions and Cl minus ions ratio. Total number of Na plus ions and total number of Cl minus ions ratio. So you will get the same number. The number of Na plus ions will be equal to number of Cl minus ions in any amount of sodium chloride crystal. For example, in this crystal, I got some X particles of Na plus and X particles of Cl minus. So X cancel, right? 1:1 ratio. 1:1 ratio. So one Na plus ion and one Cl minus ion is there in any amount of crystal. So this 1:1 ratio is taken as a formula, that is NaCl. So this is formula unit. Right? So the main difference is in covalent molecules are discrete molecules. Take some amount of water. In the given amount of water, H2O, discrete molecules, individual molecules are there. All these molecules are attracted by intermolecular forces. Take sulfur dioxide gas. In sulfur dioxide gas, we have SO2, that huge number of SO2 molecules are there, and they are attracted by intermolecular forces. If intermolecular forces are very high, it is available in solid state. Intermolecular forces are medium, it is available in liquid state. Intermolecular forces are very less, that is available in gaseous state. So in covalent compounds, there are individual molecules, discrete molecules. But in ionic compounds, we don't have discrete molecules. We don't have NaCl. We don't have NaCl. So we have Na plus and Cl minus ion, and this Na plus ion is surrounded by 6 Cl minus ions, and Cl minus is surrounded by 6 Na plus ions. There is no NaCl. There is no individual NaCl unit. So why do we say this is NaCl? Means the ratio of number of Na plus and Cl minus ions in any amount of crystal is 1:1. That's why NaCl. If I take magnesium chloride, crystal, any amount. and take the ratio of number of magnesium ions and total number of chloride ions, you will get 1:2 ratio. That's why its formula is MgCl2. So molecular mass is, the term molecular mass is used for only molecules. Covalent compound contains molecules, and the term formula mass is used for ionic compounds. Ionic compounds do not have molecules, they have formula units. That's why it is called formula mass. While solving problems, we don't see any difference between molecular mass and formula mass. Even for CaCO3, we used to say molecular weight of calcium carbonate. For calcium sulfate, molecular weight of calcium carbonate. Nothing wrong. Right? So while doing calculations, we can use molecular weight or formula weight, any term we can use. But if there is any theoretical question, you should know that both terms are not same. So for theoretical questions, it is important. For calculations, you do anything, no problem. Three different types of atomic mass: absolute atomic mass, relative atomic mass, and gram atomic mass. And fourth one is also there. At last we will see, that is average atomic mass. So absolute atomic mass means this is the actual mass of an atom. One particular atom, the actual mass is absolute atomic mass. This absolute atomic mass units are AMU, atomic mass unit, or unified mass U. Relative atomic mass means it is how many times heavier than 1 AMU. Previously, how many times heavier than 1 hydrogen. Now it is how many times heavier than 1 AMU. So it is a relative property. Relative property does not have units. For relative properties, no units. Any relative property, no units. Specific gravity, relative property, no units. Vapor density, relative property, no units. Electronegativity, relative property, no units. So for any relative property, no units. So same calcium I am taking. What is a relative atomic mass? 40. So absolute atomic mass, take it as AAM, absolute atomic mass. Relative atomic mass, take it as RAM, relative atomic mass. Gram atomic mass, take it as GAM, gram atomic mass. Right. What is gram atomic mass? Mass of 1 mole atoms. Mass of 1 mole atoms is gram atomic mass. Its units are grams. 6.022 into 10 power 23 particles mass is taken, it will come in terms of grams. But one individual particle means it is around 10 power minus 23 grams. So which is replaced by AMU, already we discussed. That is the purpose of introducing AMU. So individual atoms mass is in AMU, and mass of atoms in terms of moles, it is in grams. And when the mass is measured with respect to any particular unit, that is relative atomic mass, no units. So now I am taking carbon. Absolute atomic mass of carbon, 12 AMU. Relative atomic mass of carbon, 12. Gram atomic mass of carbon, that is 12 grams. Similarly, take oxygen. Absolute atomic mass of oxygen, 16 AMU. Relative atomic mass of oxygen, 16. And gram atomic mass of oxygen, 16 grams. So this is the difference between different atomic masses. Same as atomic mass, molecular mass is also 3 types. This is absolute molecular mass, this is relative molecular mass, and this is gram molecular mass. The actual mass of a single molecule is absolute molecular mass, units are AMU. Relative molecular mass means how many times it is heavier than AMU. Relative molecular mass, no units. Mass of 1 mole of molecules, that is gram molecular mass, units are grams. Example, I am taking carbon dioxide. Carbon dioxide. Absolute molecular mass of carbon dioxide 44 unified mass U or AMU. Relative molecular mass 44. Absolute gram molecular mass is 44 grams. Similarly, take ammonia. Absolute molecular mass, one ammonia molecule mass is 17 U. Relative molecular mass of ammonia with respect to AMU, that is 17. Gram molecular mass of ammonia, 1 mole ammonia molecule's mass, it will come in grams, that is what? 17 grams. Now, coming to another important part, density. So we have absolute density, relative density, right? For solids and liquids, relative density is called specific gravity. For solids and liquids, relative density is called specific gravity. For gases, relative density is called vapor density. So now here I have divided the density into two parts. Separate study and separate classification. Solids and liquids, one classification, and gases, another classification. For solids and liquids, we have absolute density and relative density. Absolute density means the actual density of the molecule. How it is calculated? Mass by volume. What is its unit? Grams per cc. Mass unit is grams and volume unit is cc in CGS system. SI system, mass is in kilograms, volume is in meter cube, kg per meter cube or grams per cc. Here, conversion units. 1 gram per cc is equal to 10 cube kg per meter cube, 1000 kg per meter cube. Useful for conversions. Anyway, for solids and liquids, I am taking absolute density and relative density. Absolute density is the actual density of the given solid or liquid. Its units are grams per cc or kg per meter cube. Relative density means how many times it is more denser than density of water. Relative density, relative property means definitely we will take one standard reference. Here water is reference. So how many times the given substance is more denser than water, that is relative density. It does not have units. So relative density of solids and liquids is also called as specific gravity. In questions they will give specific gravity. They don't mention it as density, but actually it is what? Density. Now coming to gases. Even in gases, we have two different types of density, that is absolute density and relative density. So absolute density is actual density of the given gas. So mass of the gas divided by volume of the gas. Units are grams per cc and kg per meter cube. 1 gram per cc is equal to 1000 kg per meter cube. Now relative density means here our reference is hydrogen gas. How many times the given gas is more denser than hydrogen gas? That is relative density of gas. This relative density of gas is called as vapor density. Relative density of a gas is called vapor density. It's a relative property, no units. Our reference is hydrogen. See, compared to solids and liquids, gas density is very less. That's why we are not taking water as a reference. For solids and liquids, water is taken as reference. For gases, hydrogen, the lightest gas, hydrogen is taken as reference. So I think you understood the difference between these two, right? For solids, to measure relative density, our reference is water. For gases, to measure relative density, hydrogen is our reference. So gases relative density is vapor density, solids and liquids relative density is specific gravity. Both are not having units. In exam they will mention like this. Right. Now coming to this vapor density, one very important point in this vapor density, I am taking this formula. Vapor density is equal to density of the I am taking this formula. Vapor density is equal to density of the given gas divided by density of hydrogen. This is our formula. So consider the gas is 1 mole, the given gas is 1 mole and hydrogen is also 1 mole. So we have to take equal quantities. I am taking 1 mole hydrogen and 1 mole gas. Their density ratio is vapor density. Assume we have taken these two gases, unknown gas and hydrogen gas at STP. Now, vapor density is equal to, what is the density of gas? I am taking their absolute densities, mass by volume of given gas divided by mass by volume of hydrogen. So 1 mole of any substance, mass is equal to its gram molecular weight. So gram molecular weight of that gas, and here volume of gas, this is volume of hydrogen gas. Volume of unknown gas, volume of hydrogen gas, both are 1 mole. According to Avogadro's law, equal volumes of all gases contains equal number of equal volumes. According to Avogadro's law, equal volumes of all gases contains equal number of particles. So here 1 mole particles are there, unknown gas 1 mole particles are there, and hydrogen gas also 1 mole particles are there. 1 mole volumes are same and these volumes are cancelled. Once again, see, vapor density is mass by volume. So mass of unknown gas divided by volume of hydrogen gas, volume of unknown gas, and mass of hydrogen gas divided by volume of hydrogen gas. This is 1 mole, this is 1 mole. Their volumes are same, cancelled. What is left? Mass of unknown gas divided by mass of hydrogen gas. So mass of 1 mole of any gas is equal to its gram molecular weight. So gram molecular weight of gas divided by gram molecular weight of hydrogen. What is the gram molecular weight of hydrogen? That is 2. Gram molecular weight of hydrogen is 2. Now, gram molecular weight is equal to 2 into vapor density. This is how this formula is derived. We know gram molecular weight is equal to 2 into vapor density, or vapor density is equal to gram molecular weight divided by 2. So this formula is derived from vapor density formula. What is the vapor density formula? Density of gas divided by density of hydrogen. I mean density of given gas divided by density of hydrogen. How many times the given gas is more denser than hydrogen gas is relative density or vapor density. And from this formula, we got a formula. Vapor density is equal to gram molecular weight by 2 and gram molecular weight is equal to 2 into vapor density. Remember, this is applicable for gases, only gases. Now, coming to average atomic mass and average molecular mass. We have seen 3 different types of atomic mass already. Absolute atomic mass and relative atomic mass and gram atomic mass. Now I am coming to average atomic mass. So this term average atomic mass is used for isotopes. This is used for isotopes. The elements which are having isotopes, mass cannot be taken directly. I mean any one particular isotope mass cannot be taken as atomic mass. right? Suppose I have chlorine 1735 and chlorine 1737. Chlorine has two isotopes. Isotopes means same atomic number, different mass numbers. First isotope atomic mass is 35, second isotope atomic mass is 37. But what is the atomic mass of chlorine? Is it 35? No. Is it 37? No. What is the atomic mass? 35.5. Chlorine atomic mass is 35.5. It is not 35, it is not 37. What is this 35.5? Average atomic mass. This is average atomic mass. So whenever the element has two or more isotopes, its atomic mass cannot be taken directly. Its atomic mass is not the atomic mass of any particular isotope. We have to take average atomic mass. How do you take average atomic mass? Use this formula. Average atomic mass M is equal to M1x1 plus M2x2 by x1 plus x2. Where M1 and M2 are atomic mass of given isotopes. X1 and x2 are, they may be percentage abundance or mole fractions or ratios. Let us take one example to understand this formula. Here, chlorine 35 percentage abundance is 75. Chlorine 37 percentage abundance is 25%. This is 25%. I want average atomic mass. To find our average atomic mass, this percentage should be given. In questions, either percentages or mole fractions or ratios they will give. So percentage means 75, 25. Mole fraction means they will give 3 by 4, 1 by 4. Ratios means they will give 3:1. 3:1. In terms of ratios, they will give 3:1 ratio. Both isotopes are in 3:1 ratio. In terms of percentages, first isotope 75%, second isotope 25%. Find the average atomic mass. In terms of mole fraction, first isotope 3/4 and second isotope 1/4. Find its average atomic mass. The questions will be like this. Anyway, let us solve this problem with these percentages. Now, average atomic mass M is equal to, what is M1? 35. 35 into 75 plus 37 into 25 divided by x1 plus x2. x1 plus x2. 75 plus 25. Solve this. You will get approximately 35.5. 35.5. Right? In some cases, there will be 3 isotopes. Then you can extend this formula. M is equal to M1x1 plus M2x2 plus M3x3 divided by x1 plus x2 plus x3. You can extend this formula for any number of isotopes. Next, another important point is, take carbon isotopes. Carbon 12, carbon 13, carbon 14. Similarly, hydrogen isotopes. H11, H12, H13. Protium, deuterium, tritium. First I am coming to carbon isotopes. What is the atomic mass of carbon? We will take 12. We used to say 12. So this carbon 13 and carbon 14 percentage abundance is negligible, 0.000 like that. So in such cases, you can take this atomic mass directly. Same concept for hydrogen also. There are 3 isotopes for hydrogen: protium, deuterium, tritium. What is atomic mass of hydrogen? 1. Deuterium and tritium percentage abundance is very less. So no need to go for average atomic mass. So hydrogen atomic mass is what? 1. I am taking boron. Boron 510 and boron 511. Its average atomic mass is given as 10.8. Find the percentage abundance. Find the percentage. In the previous case, percentage abundances are given. They asked to calculate average atomic mass. Now, average atomic mass is given. We have to find the percentage abundance. Your same formula. What is that formula? M is equal to M1x1 plus M2x2 divided by x1 plus x2. Average atomic mass is 10.8. First isotope mass is 10. What is its percentage abundance? I don't know. Take it as x. What is M2? 11. What is a percentage abundance of boron 11? We don't know. Take it as 100 minus x. Total percentage is what? 100. So when first one is x, second one will be 100 minus x. So total percentage is 100. So here you can calculate x, you can calculate 100 minus x. So by solving this, you will get percentage abundances. Right? So here two types of problems we can expect. What is that? When percentage abundance is given, we have to find average atomic mass. When average atomic mass is given, we have to find percentage abundance. This average atomic mass concept is applicable for elements which are having isotopes. When all isotopes except one, all other isotopes percentage abundance is negligible, then no need of taking this average atomic mass concept. So you can go with the higher percentage, maximum percentage isotope mass as atomic mass. Similar to average atomic mass, we have average molecular mass. Same formula. M1x1 plus M2x2 by x1 plus x2. For 3 molecules, you can extend this formula like M1x1 plus M2x2 plus M3x3 divided by x1 plus x2 plus x3. You can extend this formula. M1, M2 are molecular masses of molecules. X1, X2 are percentage or ratio or mole fraction. To understand this formula, I will take a simple example. In a container, we have two gases, carbon dioxide and nitrogen gases. Carbon dioxide and nitrogen gases. This carbon dioxide nitrogen gases are in 3:4 ratio. Find the molecular mass of the mixture. Find the molecular mass of mixture. Molecular mass of mixture means average molecular mass. They will ask like this. So we have two gases in a container, carbon dioxide and nitrogen, two gases, they are in 3:4 ratio. We have to find molecular masses. Right. Formula M is equal to M1x1 plus M2x2 divided by x1 plus x2. What is M1? Carbon dioxide molecule first gas, that is 44. And what is x1? 3:4 ratio, this is 3. And what is M2? Nitrogen molecular weight 28. And what is x2? That is 4. And divided by sum of the ratios 3 plus 4, that is 7. So by solving this, you will get average molecular mass or molecular mass of the mixture. So when two gases are given or 3 gases are given, so how do you find the mixture molecular mass? Means average molecular mass. Next, here you can see 1 to 30 elements, their atomic mass. These are exact or accurate atomic mass, and this is approximate atomic mass. So this approximate atomic mass is required. Hydrogen 1, helium 4, lithium 7, beryllium 9, like that. You should know first 30 elements atomic masses. Higher elements, higher molecules atomic masses will be given in the questions itself. Suppose one problem is related with silver. Silver atomic mass they will give 108, silver 108. Some questions are related with iodine. Iodine 127 they will give. So you just check PYQs, previous year questions. For NEET or JEE, check previous year questions. So beyond 30, if any particular element is given, that atomic mass, any particular question is asked based on higher elements. So their atomic masses will be given. Bromine 80. But first 30 elements atomic masses they don't give. This one you have to study. So all 30 elements, their exact atomic mass and approximate atomic masses are given. So these are approximate atomic mass. So these are very important. Next, here I want to explain one very important concept regarding atomic mass. See, I am taking hydrogen. So let us now we are going to see the difference between atomic mass and mass number. Difference between atomic mass and mass number. So what is the atomic mass of hydrogen? 1. What is the mass number of hydrogen? That is also 1. Is there any difference? Yes, there is a difference. Now, coming to hydrogen. In hydrogen, 1 electron is there, 1 proton is there, and 0 neutrons. Mass of electron 0.00055 AMU. And mass of proton 1.007 AMU approximately. And mass of neutron 1.008 AMU in terms of AMU. So proton mass, and add all these things. Add all these things. I mean, this is electron mass, this is proton mass, this is neutron mass. In hydrogen, no neutrons, only proton and electron are there. Electron mass is 0.00055 and proton mass is 1.007. Add this 557,001. So this is approximately 1.008. So this is the exact atomic mass of hydrogen. If you want to calculate it for helium, in helium we have 2 electrons, 2 protons and neutrons also there, 2 neutrons. So 2 into is mass of electron, 2 into mass of proton, 2 into mass of neutron. Add all these things, you will get exact atomic mass, exact mass of helium. But instead of 1.008, simply we will take 1. Instead of 4.003, simply we used to take 4. Why we are taking 4 now? This electron mass is negligible. 0.000 electron mass is negligible. And proton mass is 1.007, means approximately it is taken as 1. Neutron mass is 1.008, approximately it is taken as 1. So approximately electron mass is negligible, we don't consider. Proton mass is 1 unit, neutron mass is 1 unit. So in hydrogen, electrons negligible, don't count. Neutrons not there, only 1 proton is there, 1 AMU. In helium, electrons not considered. We have 2 protons and 2 neutrons, 2 AMU, total 4 AMU. So this number is mass number. This number is mass number. We used to take it as atomic mass also, because it will not have fractions. Except elements with the isotopes, remaining all cases, there won't be any fractions. I hope it is clear. So the sum of the mass of electron, mass of proton and mass of neutrons is equal to accurate molecular mass, accurate mass of that particular atom. But approximately, if you consider electron 0 AMU, proton 1 AMU, neutron 1 AMU, based on this if we calculate the mass, that is approximate mass, and this is only mass number, atomic mass or mass number, approximate value. So this is how atomic mass is calculated for every element and molecules also. Next, how do you calculate molecular mass? I am taking H3PO4. H3PO4, there are 3 hydrogens. Each hydrogen atomic mass is 1. And phosphorus, 1 phosphorus atomic mass is 31. And oxygen atomic mass, each oxygen atomic mass is 16. And if you calculate it, you will get 98. So this H3PO4, one molecule means this H3PO4, 1 molecule means it is 98 AMU. This H3PO4 1 mole means 1 mole, that is 98 grams. And if they ask relative molecular mass, simply you will say 98. We don't say grams or AMU, simply you will say 98. Anyway, here important thing is some examples molecular masses I have given. So methane 16, ammonia 17, carbon dioxide 44, sulfuric acid 98, phosphoric acid 98, calcium carbonate 100, sodium carbonate 106. Right? Like this, you should know molecular masses. Every time while solving problems like this, 3 into 1 plus 1 into 31 plus 4 into 16, like this calculation is difficult, it is time taking. Especially for NEET exams, time is very important. JEE will have sufficient time. If you know problem, you can solve it. Much time will be there. That depends on your strategy. But NEET means the time will be very less. So that's why these molecular masses you should know. SO3 means you should say 80. SO2 means you should say 64. Chlorine means you should say 71. So the most familiar or most repeated molecules, molecular masses you should know. So don't go for calculations like this. Now, unit conversions. Here we have to study temperature units, pressure units, volume units. There are different units and conversions are very important in mole concept and other physical chemistry problems in chemistry. Right. Now coming to temperature. So there are three different scales: Celsius, Kelvins and Fahrenheit. So in chemistry problems, throughout chemistry, we should use Kelvin scale. We don't use Celsius, we don't use Fahrenheit. If any temperature is given in the Celsius, convert it into Kelvins. If any temperature is given in Fahrenheit, convert it into Kelvin scale. Right? How do you convert these temperatures? Here we have a relation. That what is that relation? C by 5 is equal to F minus 32 divided by 9 is equal to K minus 273.15 divided by 5. This is our relation. Suppose I have 25 degrees Celsius. 25 degrees Celsius temperature is given. I should convert it into kelvins. Use these two relations. 5 cancel. C is equal to K minus 273 to exactly 273.15, exactly 273.15, but you can use 273. It's fine. So C is 5 cancel. C is equal to K minus 273 and K is equal to degree Celsius is 25 plus 273, that is what? 298 kelvins. 25 degrees Celsius. Suppose Fahrenheit is given. Fahrenheit. So Fahrenheit means take this relation. What is that? F minus 32 by 9 is equal to K minus 23.15 divided by 5. I want Kelvin scale from this. K is equal to 5 by 9 into F minus 32 plus 273.15. If Fahrenheit 100 is given, 100 minus 32 plus 273.15. 5 by 9 into 100 minus 32 plus 273.15. This is how we are converting Fahrenheit into Kelvin scale and degree Celsius into kelvins. Right? Now I am coming to the most important point. That is what? Absolute zero. Absolute zero. So the temperature at which all molecular motions are ceased. The temperature at which kinetic energy of the gas is zero. Kinetic energy of the substance is zero. All molecular motions are ceased. That particular temperature is absolute zero. Absolute zero temperature is the lowest possible temperature minus 273.15, which is taken as 0 kelvins. The lowest possible temperature is minus 273.15. It is 0 kelvins. So minus 273.15 degrees Celsius is the lowest temperature. Further lower is not possible. Even today we did not reach the exact value of minus 273.15. We are close to the temperature but we didn't reach. Anyway, the lowest value is what? Minus 273.15. If I take that minus 273.15 as 0 kelvins, there is no negative temperatures. So here what I am trying to say, to avoid negative temperatures in calculations, the lowest possible temperature, negative temperature, minus 273.15 degrees Celsius is taken as Kelvin scale. So in Kelvin scale there is no negative value. In degrees Celsius negative temperatures are there, but in Kelvin scale no negative temperatures because the least possible value is taken as 0 kelvins. Right? So absolute zero means the temperature at which kinetic energy becomes zero, the temperature at which all atomic and molecular motions are ceased, and the lowest possible temperature is absolute zero temperature. Next, coming to volume conversions. Volume of a gas is measured by idiometer. Gas volume is measured by idiometer. So volume conversions here you can see 1 decimeter cube is equal to 1 liter. 1 decimeter cube is 1 liter. 1 meter cube is equal to 1000 liters. 1 centimeter cube is equal to 1 ml. Here SI unit of volume is meter cube. CGS unit of volume is centimeter cube or ml. Centimeter cube means 1 milliliter. Common units of volume is liters. So liter is common unit. It is not SI unit, it's not CGS unit. Right? In gas problems, titration problems, we are using volume in liters. But SI unit means it is meter cube, CGS unit means it is centimeter cube. These conversions are 1 decimeter cube, 1 liter, 1 meter cube, 1000 liters, 1 centimeter cube, 1 milliliter, and other conversions you can see here. Next, coming to pressure conversions, another important part, pressure. Atmospheric pressure is calculated by barometer. Atmospheric pressure is calculated by barometer, and the formula is P is equal to H rho Z. H is a rise in mercury level in the test tube. Rho is the density of mercury, and G is gravity. So atmospheric pressure P is equal to H rho Z. But pressure of a specific gas is measured by manometer. This is manometer. Gas pressure is measured by manometer and atmospheric pressure is measured by barometer. So there are two different manometers. In physics also you will study that. Open end manometer and closed end manometer. So open end manometer means its formula, pressure of a gas is equal to atmospheric pressure plus H rho Z. This is open end manometer. Closed end manometer means what we will get? Atmospheric pressure is equal to atmospheric pressure minus pressure of the gas is equal to atmospheric pressure minus H rho Z, plus or minus H rho Z, whatever it is. Specific gas pressure is measured by manometer and atmospheric pressure is measured by barometer. Now pressure conversions. Here SI unit of pressure is Pascal. Pascal or Newton meter square. Pascal or Newton per meter square. CGS unit of pressure is dynes per centimeter square. CGS unit is dynes per centimeters. SI unit is Pascal or Newton per meter square. Right. Common units. Atmosphere, bar are common units. 1 atmosphere is approximately equal to 1 bar. 1 atmosphere is approximately equal to 1 bar. Right. Here 1 atm is equal to 1.01 bar. or 1 bar is equal to 0.98 atmospheres. 1 bar is 0.98 atmosphere, 1 atm is 1.01 bar, approximately both are equal. Right. So other conversions here. So 1 bar is equal to 10 power 5 pascals. 1 pascal is equal to 1 Newton per meter square. Newton per meter square, Pascal, both are same. 1 atmosphere is equal to 760 millimeters of mercury. Here 1 atmosphere is equal to 76 centimeters of mercury. So 76 centimeters of mercury means 760 millimeters of mercury. Coming to three different constant values: universal gas constant, laschmidt number, and Boltzmann constant. First, I am coming to universal gas constant. This is ideal gas equation. Ideal gas equation, PV is equal to nRT. PV is equal to nRT, ideal gas equation. So from this formula, N is equal to PV by RT. P is the pressure of gas, V is the volume, and R is a universal gas constant, and T is a temperature. Gas constant R is equal to PV by NT. PV by NT. When I substitute pressure in atmospheres, volume is in liters, substance in moles, temperature in Kelvin scale, the gas constant value is 0.0821 liters atmospheres per Kelvin mole. Right? In the ideal gas equation, pressure is in atmosphere, volume is in liters, amount of substance is in moles, and temperature in kelvins. So that we'll get a constant value. That constant value is 0.0821 liters atmospheres per Kelvin mole. In gas loss problems, ideal gas problems, this unit is useful. If pressure is substituted in a SI unit, Newton per meter square or pascals, volume is substituted in meter cube, moles in moles only, temperature in Kelvin scale. So we'll get SI unit. R value in SI unit, that is 8.314 joules per Kelvin mole. In chemical kinetics and other some physical chemistry topics, we are using this value 8.314 joules per Kelvin mole. So when pressure and volume are given in the SI unit, 8.314 joules per Kelvin. If pressure and volume are given in CGS system, that is 8.314 into 10 power 7 x. 1 joule is equal to 10 power 7 x. Next, in terms of calories. So in energy related problems, we are using common unit calories also. So in calories, 2 calories per Kelvin mole. So we can convert joules into calories. So 1 calorie is equal to approximately 4.2 joules. 4.18 joules, 4.2 joules. So you can go for these conversions. So in terms of calorie, universal gas constant value is 2 calories per Kelvin mole. In SI units, 8.314 joules per Kelvin. When pressure and volume are given in common units, 0.0821 liters atmosphere per Kelvin. So for any gas, for any substance, this R value is fixed. So that's why it is called universal gas constant. Some constants are not fixed for all substances. They are called as constants only, but not universal constants. This is universal constant. Next, I am coming to laschmidt number. Laschmidt number. What is laschmidt number? So we know avogadro number. 6.022 into 10 power 23 particles is avogadro number. Right? Here 6.022 into 10 power 23 molecules present in 22.4 liters volume at STP. At STP, in 22.4 liters volume, how many molecules are there? 6.022 into 10 power 23. Right, this is in liters. Now, in 1 ml, how many particles are there? 22,400 milliliters of gas contains Avogadro number of particles. 1 ml of gas contains how many particles? That is laschmidt number. That laschmidt number is 2.687 into 10 power 19. 22,400 ml of gas contains Avogadro number of particles, Avogadro number of molecules at STP. So at STP, 1 ml of gas contains how many particles? That is laschmidt number 2.687 into 10 power 19. The molecules in 1 centimeter cube of ideal gas at STP. Coming to Boltzmann constant. Boltzmann constant. So we know universal gas constant R. Universal gas constant R. So what is this Boltzmann constant? R by N is a Boltzmann constant. R is universal gas constant and N is a Avogadro number. See this unit. Universal gas constant units 8.314 joules per Kelvin mole. This constant is per mole, per 1 mole of gas. This constant is per 1 mole of gas. This constant is per 1 mole of gas. Here, this is divided with Avogadro number of molecules, means this is per molecule. Right? Universal gas constant per molecule, per single molecule is Boltzmann constant. This constant is per mole. This constant is per molecule, Boltzmann constant. So 8.314 is R value, Avogadro number 6.022 into 10 power 23. This calculated value is what? 1.38 into 10 power minus 23. Boltzmann constant. Next, coming to molar and gases one. So what is molar volume? What is molar volume? Volume of 1 mole gas is molar volume. Volume of 1 mole of any gas, carbon dioxide, hydrogen, nitrogen, volume of 1 mole of any gas is molar volume. At STP, this molar volume is 22.4 liters and this is the old value. How do you get 22.4 liters? Here, the standard pressure is taken as 1 atmosphere. Standard pressure is taken as 1 atmosphere. So, ideal gas equation PV is equal to nRT. I want volume. Volume V is equal to nRT by P. Right? And this pressure is 1 atm at standard conditions. But modern value, standard pressure is 1 bar. Standard pressure is 1 bar. 1 atmosphere, 1 bar approximately same, but 1 bar is equal to 0.98 atmospheres. 1 bar is equal to 0.98 atmosphere. Previously, if pressure is 1 atm, you are substituting 1 atm. Now, pressure is 1 bar. 1 bar means 0.98 atmosphere. This is slightly smaller value. When denominator is smaller, whole value increases. Now, here 0.98. If you calculate it, that's standard molar volume is 22.7. So, 22.7 to be followed. Even in books, questions are solved with 22.4 liters only, but right now all NEET and JEE questions are with 22.7. So standard molar volume at STP is 22.7, old value is 22.4. The difference is previously standard unit of pressure is 1 unit, now standard unit of pressure is 1 bar. Next, atomicity. The number of atoms present in one molecule is atomicity. This atomicity is useful in the calculation of total number of atoms. Noble gases are monoatomic. Helium, neon, argon, krypton, xenon, they are monoatomic. Atomicity is 1. O2 and 2 diatomic. Atomicity is 2. P4, CH4, S8, they are polyatomic molecules. P4 atomicity 4, CH4 atomicity 5, S8 atomicity 8, and Buckminster-Fullerene C60, 60 is the atomicity. And where we are using this atomicity to calculate the number of atoms. So number of atoms is equal to number of molecules into atomicity. Number of atoms is equal to number of molecules into atomicity. For example, I am taking sulfuric acid. 100 molecules of sulfuric acid I have. 100 molecules. I have to find the total number of atoms. Total number of atoms is equal to how many molecules are there? 100 molecules. In each molecule, how many atoms are there? 2 plus 1 plus 4, total 7. We have 100 molecules. In each molecule, 7 atoms are there. 2 hydrogens, 1 sulfur and 4 oxygen. 7 atoms are there. So 100 into 7. So 700 atoms. So this is how we are using atomicity in the mole concept. So number of atoms formula, total number of molecules into atomicity. What is atomicity? Number of atoms present in one molecule. So coming to very important formulas related to mole concept. So to solve mole concept problems and to solve many physical chemistry questions, these formulas are important. Number of gram atoms is equal to number of moles of atoms. Number of gram molecules is equal to number of moles of molecules. Suppose 10 gram atoms given. 10 gram atoms means not 10 grams, that is 10 moles of atoms. 20 gram molecules are given. So it is not mass, it is not 20 grams. 20 gram molecules means 20 moles of molecules. So formulas to find number of moles. In terms of weight, weight by gram molecular weight. In terms of particles, given number of particles by Avogadro number of particles. In terms of volume, given volume by gram molar volume. At STP, given volume by 22.7 liters. Right? Gram molar volume is volume of any gas. Volume of 1 mole of any gas is gram molar volume. So volume of 1 mole of any gas at STP is 22.7 liters. So old value is 22.4, but the perfect value is 22.7. In terms of molarity, number of moles is equal to molarity into volume in liters. Millimoles means molarity into volume in milliliters. Moles formula, molarity into volume in liters. Millimoles formula, molarity into volume in milliliters. And total number of molecules, moles into Avogadro number. And total number of atoms formula, moles into Avogadro number into atomicity. Atomicity is the number of atoms present in one molecule. And number of particles, total number of moles into Avogadro number into number of particles present in one molecule. Here particles can be atoms or electrons or protons or neutrons or nucleons or valence electrons. It can be anything. For example, I want to find total number of electrons. Total number of electrons is equal to moles into Avogadro number into number of particles in one molecule. I want valence electrons, the given amount of substance. So total number of valence electrons is equal to moles into Avogadro number into valence electrons in one molecule. Right. So by using these formulas, let us solve one important example. That is, find moles, molecules, atoms, nitrogen atoms, electrons, and valence electrons in 170 grams ammonia. We have to find moles, molecules, atoms, Avogadro nitrogen atoms, electrons and valence electrons. First, let us find number of moles. Weight is given. Given weight by gram mole per minute. Given weight is 170 by 17. This is what? 10. 10 moles are there. 170 grams of ammonia means that is 10 moles. Now, molecules. Molecules is equal to formula moles into Avogadro number. How many moles are there? 10 moles. Avogadro number is what? 6.022 into 10 power 23. We can simplify this. First moles, second molecules. Next, coming to atoms. Total number of atoms is equal to moles into Avogadro number into atomicity. Total number of moles 10. Avogadro number 6.022 into 10 power 23. Atomicity, number of atoms in one molecule. Nitrogen is one atom and 3 hydrogens are there. So 3 plus 1 4. Atomicity is 4. So by simplifying this, you will get total number of atoms. Next, nitrogen atoms. Nitrogen atoms. Only nitrogen atoms I want to find. In 170 grams of ammonia, how many nitrogen atoms are there? Moles into 10. Avogadro number 6.022 into 10 power 23. And how many nitrogen atoms are there in one molecule? Only one nitrogen. So into 1. So you will get answer. Now electrons, valence electrons we have to find. First let us take electrons. Nitrogen atomic number 7. So it has 7 electrons. Hydrogen atomic number is 1. Each hydrogen 1 electron, 3 hydrogens, 3 electrons, total 10 electrons. 10 electrons are present in one molecule. Now coming to valence electrons. Valence electrons. So what is nitrogen configuration? Nitrogen electronic configuration 1s2, 2s2, 2p3. This 2s2, 2p3 is the valency shell. Number of electrons in the valency shell, valence electrons 2 plus 3 5. So nitrogen 5 valence electrons, each hydrogen 1 valence electron, 3 hydrogen 3 valence electrons, 5 plus 3 8. Valence electrons are 8. So 1 ammonia molecule, valence electrons are 8. 1 ammonia molecule, total number of electrons are 10. I have a formula. Total number of particles. Total number of particles is equal to moles into Avogadro number into number of particles in one molecule. Number of particles in one molecule. So if our question is electrons, instead of particles take electrons. So total number of electrons is equal to moles 10. Avogadro number 6.022 into 10 power 23. And number of particles, number of electrons in one molecule 10. Substitute 10 here, you will get answer. If it is proton, substitute number of protons in one ammonia molecule, you will get answer. Right. If you want valence electrons, substitute number of valence electrons in one molecule. That is what? 8. Substitute 8, you will get answer. What is that answer? Total number of valence electrons is equal to 10 moles into 6.022 into 10 power 23 into 8. 8 valence electrons in one molecule. Right. So this is our mole concept theory part. In the next lecture, we will discuss mole concept questions. Right? Nearly 30 questions we are going to discuss in the next lecture. So these 30 questions covers previous year questions and important models. Right? All important models and previous year questions will be covered within 30. That is very useful for your mole concept revision. Our previous lecture is laws of chemical combination. If you want, you can see. Okay. Thank you.